Today, my group and I are going to talk about the applications and possibilities of auxetics. So you're probably thinking, what are auxetics? Auxetics are materials that exhibit negative Poisson's ratio. What is negative Poisson's ratio? Well, that begs the question, what is Poisson's ratio?
Poisson's ratio is the ratio between lateral strain and longitudinal strain. Most materials found in nature exhibit a positive Poisson's ratio, where an increase in lateral strain would decrease longitudinal strain, and vice versa. What does this all actually mean? Well, simply, the material gets thinner when stretched and fatter when compressed. However, auxetics do the opposite. Due to their unique structure, auxetics get fatter as you stretch them and thinner as you compress them. Before talking about how auxetics work, let's have a look at a normal material, like a rubber band, demonstrating a positive Poisson's ratio. There are few materials in nature that demonstrate negative Poisson's ratio. There are some tissues in the body, certain rocks and minerals, and some polymeric honeycombs. The concept of a material behaving this way is against instinct, since the material would have to change its inherent density as it was either stretched or compressed. So, in order to achieve this property, specific structures and patterns are used, and they change the innate properties of a material. Many different structures have been discovered that can all achieve different values for negative Poisson's ratio. In this video, we will only be looking at a couple of different structures for applications, including the snowflake structure, which we are about to demonstrate. Here you can see the snowflake structure stretching in the lateral direction as it is loaded axially. We chose to show you this structure because it was very unique to the rest of the designs we encountered, and we really just thought it looked cool. And it also gets the point across.
One of the most promising advances with the use of auxetic structures are for the padding and energy-absorbing applications in sports. The most important part of sports is the safety of the players. Injuries can lead to permanent damage, such as in the NFL where concussions are prominent. Studies show that auxetic foams significantly minimize acceleration compared to a conventional open-cell polyurethane counterpart that is typically used for many sport and compression uses. As seen in the graph below, peak acceleration was almost 3 times lower in negative Poisson's ratio material at higher impact energies. This could be revolutionary for equipment like helmets, which have a restricted amount of space and need to greatly reduce impact acceleration in order to combat dangerous head injury and concussions.
Auxetics can also be used in many public safety applications. Our roadways are constantly developing cracks and potholes due to excessive loading, daily temperature changes, and a number of other reasons associated with the installation of asphalt. You're probably wondering, how can auxetics help? Well, if an auxetic is used to fill the crack or hole, and then the size of that crack or hole changes, the auxetic will better adapt to the new size of the crack or hole. If a crack or hole gets wider or larger, you want the fill material to expand both laterally and axially in order to fill the entire space. A normal material would shrink in the middle as the hole got larger and would not be functional anymore and have to be replaced. Crack and pothole mitigation can lead to better road safety by decreasing the amount of accidents caused by dangerous road or highway conditions.
Not only can auxetics help reduce the number of accidents on the road, but they can also decrease the primary danger associated with accidents. This has led to some car bumpers being designed to have negative Poisson's ratio. We discussed already the shock-absorbing properties and the ability to decrease acceleration on impact for these materials, and they can greatly reduce the injury upon impact in an accident. Slowing the acceleration upon impact is vital to safety. There is a reason it is a major concern for car developers, and it is the cause for cars to have frames that crumple in the front. An auxetic bumper would coordinate well with the crumpling frame to decrease the overall acceleration felt by the passengers.
Auxetics also have possible military defense applications. Take this armored car, for example, that is being ambushed with an IED. An auxetic barrier could mitigate the high impact force of the IED and prevent the destruction of the vehicle and possibly save lives in the process. The future of auxetic materials holds many applications in various fields such as biomedical, aerospace, and defense purposes. These fields right now have limited uses for auxetics as the materials and patterns have not been sufficiently developed. However, the possibilities are still endless. The quality of the auxetic materials to exhibit negative Poisson's ratio and behavior allows for an unlimited amount of future application.
Created using Powtoon.